Hello and welcome to this revision session on A-Level Physics Paper 3, the Astrophysics option. So in today's revision session, what we're going to be doing is looking at how to answer examination questions on A-Level Physics Paper 3. So if we've been successful and we've learnt in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and then finally understand what topics we need to improve upon for AQA A-Level Physics. So how should you be preparing and using this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than that of the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. And when you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side, write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. After the revision session finishes, write up these notes into a revision sheet for you to use independently. So what are some tips on how to revise AQA A-Level Physics? So the first step is learning the key facts, learning the knowledge of the course by using mind maps, writing notes, prep notes, class workbooks, revision guides. The second step is to test yourself. So you will need to retrieve your knowledge by using your own cue cards, using things like Seneca, Caboodle, and knowledge checkers. And the third step is to practice examination style questions. So you might want to download your exam past papers to do this. You might want to use exam prep books, homework books, study books, additional workbooks to answer exam questions and mark your own work. So the three steps of learning the key facts, testing yourself, and practicing exam style questions are how you should be revising AQA A-Level Physics. So let's have a look at some past paper examination questions for the astrophysics topic. The first questions we're going to focus on are those to do with telescopes. So the first question says, explain what is meant by the Rayleigh criterion, and then a telescope uses wavelengths in the range of 90 nanometers to 120 nanometers. Explain why this telescope must be located in space, and go on to discuss one advantage that this telescope has compared to a telescope with the same aperture that uses visible light. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this question? Well, the first one, it's just a key definition of what we mean by the Rayleigh criterion. So this is a definition you should just memorize and learn. So the Rayleigh criterion identifies the minimum possible angle subtended between two objects which can be resolved, so it can be seen as two separate objects. So this occurs when the central maximum of the diffraction pattern of light from one object coincides with the first minimum or above, of the second object. Anything less than that and the two objects cannot be resolved by the telescope. The next question, you've got to recognise at what part of the electromagnetic spectrum that those wavelengths are attributed to. So this telescope must be detecting ultraviolet wavelengths. So we can tell this because the wavelength is smaller than that of visible light being around 500 nanometers. So it must be a UV telescope. Now you've got to be aware that ultraviolet radiation is absorbed by ozone in the atmosphere, so therefore we've got to place it in space so we can actually observe this ultraviolet radiation. Now the advantage of using ultraviolet is that it will give a better resolution, because we know that the resolution links to lambda over d. If d is the same value and lambda is going to be a smaller number because it's going to be a lower wavelength than the visible light, well, therefore the resolution you will achieve, the smallest angle which you can resolve two separate objects, will be a smaller one. So you've got a better resolution. The next question says, Table 1 shows information about two telescopes. Each telescope detects radio waves with a wavelength of 21 centimeters. Compare the performances of the telescopes when both are used to observe the same faint radio objects. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this question? So I think it's very important that you use both columns of the table to answer this question. So the first thing to do is to actually look at the collecting power of each telescope. Now you've got to be aware that the collecting power is directly proportional to the area, so the diameter squared of the telescope. So you can work out the collecting power of Arecibo by doing 305 squared, and then working out the collecting power of Lovell by doing 76 26 squared, and then dividing one by the other to understand that Arecibo has a 16 times higher collecting power, so therefore it'll be easier to measure those faint objects because it has a higher power to do that. And then also you could calculate the resolutions by saying it's lambda over d, so you could do a value over 305 and a value over 76 and see that Arecibo can have a lower minimum angle of resolution, so therefore will have a greater resolution than Lovell. Okay, so therefore you can see that the Arecibo telescope, by that conclusion, will be able to observe images which are fainter and also observe the images in more detail. And then the second thing to note is you can look at the idea of the shape, so it makes it very clear that the shape of the telescope is important. So you'll see that you can get spherical aberration. So Lovell, okay, is going to have no spherical aberration because it'll be perfectly parabolic, so therefore okay, it might actually get a more detailed image, even though that Arecibo has a better resolution in theory, because Arecibo will suffer from spherical aberration. The next question says, draw a ray diagram to show how a convergent lens can cause spherical aberration, and then draw a labelled ray diagram for an astronomical refracting telescope in normal adjustment. Show 3 non-axial rays passing through both lenses and label the principal foci of those lenses. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you've just got to be able to draw diagrams of how you can show spherical aberration and chromatic aberration. So spherical aberration occurs when your curved mirror is not perfectly parabolic. So you can show this by drawing two pairs of rays parallel to the principal axis coming into that mirror, and then you'll notice that they'll reflect and meet at different points, so therefore will have different foci. Now it's important that the rays further out from the center, okay, will reflect off the mirror and then cross over and have a focus closer to the mirror than those of the inner rays. So you've got to ensure you draw that on your diagram. Now the second one is you've just got to learn how to draw your diagram for an astronomical refracting telescope in normal adjustment. So as you can see here, now it's very important to know that normal adjustment means that they share the same plane, okay, for their focal points, that same focal plane. So you'll see here FO and FE are in the same plane in the diagram. Ensure that you draw your three non-axial rays. Again, non-axial meaning they're not parallel with the principal axis, as you can see here, and show both your optical lens and your eyepiece lens. Now note, you've got to ensure that you trace back the three lines coming from the eyepiece lens to indicate what images you are receiving. So please ensure that you draw those. Remember, the dashed lines on the diagram are part of construction lines and the rays are not actually there. The next question says, the James Lick telescope is an astronomical refracting telescope. When in normal adjustment, the distance between the lenses of the telescope is 17.4 meters and the angular magnification 750. Calculate the focal length of the eyepiece lens. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, the first thing is we know the angular magnification and we know the length. So we know the angular magnification, which is FO over FE, is equal to 750. We also know that the length in total of the telescope is FO plus FE, so therefore FO plus FE is 17. So we can use this idea to sub in values. So what we can therefore say is we can say FE is going to be equal to FE plus FO over 751, because you'll notice you can work it through by looking at those terms and linking them in together. So via that logic, we can say that 17.4 over 751 is going to therefore equal FE. So FE is equal to 2.3 times 10 to the minus 2 meters. It's very important that you can sub in the equation for the total length of the telescope into the angular magnification of the telescope and vice versa. The next question says the James Lick telescope can be used to identify binary stars. Two techniques are available using the telescope, using a processed image from a CCD and a direct observation using the naked eye. Compare the use of a CCD with the use of a naked eye to observe the binary stars with this telescope. So pause the video now, then unpause the video when you want to go through your answer. Right, with these types of questions, it's important that you address each bullet point separately. Now, this question is asking you the advantages and disadvantages of CCDs compared to naked eyes to record and monitor images produced by telescopes. So what you should be aware is that the resolution is limited by the diameter of the objective lens, so it will make no difference, and that the CCD will have a better resolution due to having a smaller spatial resolution than the eye, so therefore be easier to see stars as separate objects, and you can have them in more detail. It's important to know that CCDs have a higher quantum efficiency than eyes do, so CCD is about 70, 75, 80%, the eye being about 1 or 2%, so therefore it's easy to observe dimmer objects where you don't need as many photons to hit the measuring device to register an image. Also, you've got to be aware that CCDs can detect a wide variety of wavelengths, while the eye can only observe visible wavelengths, so you can observe more binary pairs of stars. And then finally, CCDs are more convenient to use, so for example, you can store images, you can transfer images, whilst in the eye, obviously you can't do that, and you can't send these images around. Now, in addition, you might also note that CCDs have a longer exposure time than the human eye, so therefore again it's easier to observe those dimmer objects. The next question says, draw a ray diagram for a Cassegrain telescope, and your diagram should show the paths of two rays up to the eyepiece lens. The ray should be initially parallel to the principal axis. Then the second question says, a spacecraft passes Pluto at a distance of 12,500 kilometers. The telescope on board has an aperture of diameter 0.21 meters and operates at a wavelength of 450 nanometers. Discuss whether this telescope is suitable for studying a crater with a diameter of approximately 1 kilometer on Pluto. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Much like how you've got to be able to draw the diagram for a refracting astronomical telescope, you've got to be able to draw one for a Cassegrain as well. So you'll notice that you've got your two mirrors in your Cassegrain telescope. So you've got your primary mirror, your secondary mirror, and then you've finally got a lens afterwards. Now again, you've got to draw your lines parallel to the principal axis, and note that they'll reflect off the primary mirror, they'll then hit off the secondary mirror, but again remember that in that secondary mirror they won't have hit their focus yet. The focus occurs behind the mirror, and they'll then reflect off that secondary mirror, cross over before they go through a gap in the primary mirror, and then they'll hit the lens afterwards. Now the next question is asking about whether we can see if it's suitable for studying that particular diameter of crater. So what you're going to be able to do is work out the resolution of your telescope. So you can work out your resolution of telescope by using the equation that the minimum possible angle to resolve from is equal to lambda over d. So you've got your value of d, diameter of the telescope is 0.21, and you've got the wavelength of 450 times 10 to the minus 9, because we're going from nanometers to meters. So we've got our resolution to be 2.14 times 10 to the minus 6 radians. So therefore the smallest detail that we could see on the telescope is that resolution multiplied by the size of the planet, or the dwarf planet Pluto itself. So we'll do that angle times by 12.5 times 10 to the 6, so we're going to be going from 12,500 kilometers into meters. So therefore we can see our smallest detail to be 27 meters, which is about 1/40th of the crater. So therefore you can consider that you can probably study the crater to quite a good detail. Remember to always give that conclusion once you've worked out your numerical values. The next question says the Hubble telescope has an aperture of diameter 2.4 meters. Compare the collecting power of the Hubble telescope with the telescope of the spacecraft in the previous question. Then an astrophysicist had to decide whether to use a reflecting telescope or refracting telescope on the spacecraft in the previous question. Discuss which type of telescope to use. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, it's important to note that collecting power is directly proportional to the area of the dish of the telescope. Now, the area of the dish of the telescope can be linked by doing the diameter squared. So you know that the diameter of the Hubble telescope is 2.4 and of the previous telescope to be 0.21 meters. So you square both values and then find the difference in the power by ratioing them. So you do 2.4 squared over 0.21 squared, so you get a difference of 130 in terms of power. So So therefore the Hubble Space Telescope will have a much higher collecting power than the other telescope. Now in terms of which telescope to use, you'll notice that you've just got to compare and contrast reflecting and refracting telescopes. So in terms of refracting telescopes, the issues you'll have are you'll get spherical aberration and chromatic aberration. You'll also have you have your idea that refracting telescopes will need to be longer so you can get that magnification, and they'll have to be made quite heavy because you're going to have to put the supports at the sides of the telescope so they can sag, because the light has to go through the actual refracting telescopes. That's harder. And then also you're going to have the idea of it's going to be a lens, so you're going to have quite a bit of chromatic aberration. Now for reflectors, you've got to remember that the secondary mirror will block some of the radiation, so therefore it could reduce your image brightness. Again, some of the radiation has to go past the secondary mirror to get to the primary mirror, so you'll get some diffraction taking place. Now again, in the question it says, notice, don't just talk about cost or difficulty of construction, because they're not going to be issues in this particular scenario, because they're just looking at how good the image is going to be produced. And again, remember to give a conclusion on what you think the answer should be. Let's have a look at some questions to do with stars. So the first question says, figure 1 shows the evolution of a star similar to the sun on the Hertzsprung-Russell diagram. State the evolutionary stage of the star at each point, W, X, Y and Z. Then the Theta Carinae is a star with a radius 5 times that of the sun. It has a surface temperature of 31,000 Kelvin. Annotate figure 1 with a T to show the position of Theta Carinae. So pause the video now, then unpause the video when you want to go through your answer. Right, with this first question, you've just got to know where the different stages of a star's evolutionary cycle can be found on the Hertzsprung-Russell diagram. So you'll notice that the W is going to be a protostar or a gas cloud, because it's going to have quite a big brightness, but quite again a low temperature, because you haven't got that real fusion taking place yet. So it's going to be found at W is going to be the protostar. You'll see at X we're going to be starting on the main sequence. Y is going to be a red giant, again because it's a lot larger there. And then finally we're going to see Z to be the white dwarf in the bottom of the side. Now again, you're going to have to, in the second question, understand in terms of surface temperature what that links into in terms of spectral class, and then understand roughly how the change in the radius is going to affect your absolute magnitude. So you can see here that you can see where the accepted region will be. It's going to have a magnitude of less than 5, because you'll notice that it's got quite a high temperature here, so it's going to be popping up there, and it's going to have a bigger radius than the sun, but it's still going to be extremely bright, so it's going to be high up at a high negative absolute magnitude. And you should be aware that if you've got a temperature of about 31,000, it'll be in class O, so it's going to be in that top grey box region. The next question says, an astronomer suggests that an Earth-sized planet orbits Theta Carinae. Explain one difficulty with using the transit method to detect this planet. Then the astronomer suggests that the Earth-sized planet receives a similar amount of power from Theta Carinae as the Earth does from the sun. The average power output of the sun is 3.8 times 10 to the 6 watts. Determine the orbital rate of the Earth-sized planet orbiting Theta Carinae. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've just got to know the difficulties with all the different methods of detecting exoplanets. So with the transit method, the issue is that it's going to be when the planet moves in front of the star from our line of sight, so we'll block out part of the star, so we'll reduce the radiation we can receive from that star. Now, the issue is going to be the planet will be, compared to the star, very small, so therefore little light will be blocked out, especially because it's an Earth-sized planet, so not a Jupiter-sized planet, but an Earth-sized planet, so not much radiation will be blocked out by the planet, so therefore be difficult to detect. Now in terms of the second question, you can see here we've got an average power output. So what we can do is we can use our equation of P equals sigma A T to the 4. And what we can then do is we can work out the power from Theta Carinae by working it through as such by doing sigma A T to the 4. Now we know sigma is 5.67 times 10 to the minus 8. We can work out what the area is by doing 4 pi r squared. Okay, and we know that value from the previous question. Okay, and then we can also also multiply by t to the 4, and again we know the value of t from the previous question, so we get out our power from theta Caroline to be 8 times 10 to the 30. Then what you can do is ratio the two power outputs, the one from the exoplanet and the one from Earth. Then as a result we get a ratio of 2.14 times 10 to the 4, so therefore we can link it through that you can link the idea that it's going to link as a ratio because of the distances. So you can then, what you can then do is square root your answer to get 1.54 times 10 to the 2, then multiply by 1.5 times 10 to the 11 to get 2.2 times 10 to the 13 meters. Again, that's just converting your values, okay, to then get into meters by multiplying there. Now the next question says, which graph shows the light curve for a typical type 1a supernovae? So pause the video now, then unpause the video when you want to go through your answer. Right, in this question it's just a fact. You've just got to learn what the light curve look like for type 1a supernovae. So your answer is going to be D. Now the first thing to note is the scale for the light curve for supernova is in days as opposed to hours. It takes months for this to take place. Now again, at the start there's a short, sharp initial burst of radiation, so it gets a lot brighter, so it gets to a lot more negative absolute magnitude straight away, and it peaks at about minus 19, minus 20 as you can see here, and then it gently comes off over time and decreases in brightness, so the absolute magnitude gets less negative. The next question says the Andromeda galaxy is approximately 7.7 times 10 to the 5 parsecs from Earth. Deduce whether a type 1a supernovae which occurred in Andromeda can be observed from Earth with the naked eye. So pause the video now, then unpause the video when you want to go through your answer. Right, to answer this question, you're going to have to work out what your your apparent magnitude is going to be, because we're observing it from Earth, then link that into the Hipparchus scale to work out whether we would see it with our eyes. So the equation we would use is small m minus big M equals 5 log d over 10. Now again, d has to be in parsecs, so we're fine, and we've got to rearrange the equation to make small m, the apparent magnitude, the subject. So you can pop in all your numbers and you can work it through. So again, you can work out what capital M is, absolute magnitude, from the previous question where it gave you the absolute magnitude, or the peak absolute magnitude, to be about minus 19, minus 19.5. So you pop them all in, and remember, don't lose that minus sign, because that's very important. So therefore you'll get an apparent magnitude of about 5.1. Now again, you'll note that Hipparchus said that the dimmest star visible with the naked eye from Earth has an apparent magnitude of 6, so therefore in our comparative statement we would notice that you can see this from the Earth because it is at a value of at least 2.51 times brighter than apparent magnitude 6, because remember the difference between apparent magnitudes is 2.51 times, so therefore you will be able to see it. The next question says, Mia Placidus and Avior are two stars in the constellation Carina. Miscelebus is a class A star and Avor is a class K star. Figure 2 shows how the intensity of radiation arriving at the Earth varies with wavelength for one of these stars. Only the important features of the variation are shown. So deduce, with reference to figure 2, the identity of the star. So in your answer, include how you explain the overall shape of the graph, describe the processes in the star that lead to the decreases in intensity, and state the identity of the star. So pause the video now, then unpause the video when you want to go through your answer. Right, well again, with these types of questions you're going to have to address each bullet point separately in a different paragraph to logically address your answers, because you get some marks for logically addressing your statements and writing it in a sensible manner. So to explain the overall shape, you would say that it's shown the black body curve, or the black body spectrum of the star. We can then link that with our equation of lambda max and t, because we know that's going to link in by Stefan's law. We can then also indicate that it's a continuous spectrum emitted by the star, so it's emitting all parts of the electromagnetic spectrum. Now if we describe the processes in the star, why there's dips, there's going to be dips because it's part of absorption. So what happens is, as the radiation is emitted from the core of the star, that particular wavelengths are absorbed by elements in the atmosphere of that star. They're then re-emitted in random directions, leaving dark lines or absorption lines. Now the most common of these is the Balmer lines, which is produced by the excitation of hydrogen from the Ne equals 2 state. And again, the Balmer lines are famous because hydrogen is found in all stars, and the Balmer lines are the ones that are found in the visible spectrum of hydrogen. Now, which star should you conclude it is? Well, you should work out from the information given to you that Maya Placidus is a class A star, so you can then work out its temperature to be about 9,000 Kelvin. So you can then work that through, okay, and then you can see that if you look on the graph here, that you can then work out what the wavelength is going to be by using Stefan's law, and see that it's going to be approximately that of a class A star. Or the other thing you could say is you could memorize what the wavelengths of the Balmer series are at, and then we know that stars with a class A or class B are going to have really strong Balmer lines. So because there are strong Balmer lines in this spectrum, it's going to be the class A star, not the class K star, so therefore it's going to be Maya Placidus. Let's now have a look at some questions concerning cosmology. The first question says, is IC 2497 is a galaxy that contained a quasar. It is believed that the quasar stopped emitting radiation several thousand years ago. Suggest why the quasar stopped emitting radiation. And IC 2497 has a redshift of 0.0516. Determine the distance from the Earth to IC 2497 and give an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've just got to understand why quasars emit radiation in the first place. So quasars are formed around a black hole, and quasars emit radiation when matter is falling in towards the black hole. As they're accelerated towards the black hole, that acceleration causes radiation to be emitted outwards. Now, if there's no matter falling into it, there'll be no acceleration, so no emission of radiation, which is where your answer comes from. Now, in this next question, we have to use quite a few equations. So the first equation we're going to use is the redshift equation. So we know that Z is equal to V over C. Now we've got Z 0.0516 and we've got C 3 times 10 to the 8. So we can rearrange that equation to find V, which we find to be 1.55 times 10 to the 7 meters per second. We can then use our equation for the Hubble constant V equals HD to find out our value for D. So D is going to be equal to V over H. Now the first thing to note for this equation is that V has to be in kilometers per second. So we converted 1.55 times 10 to the 7 meters per second into 1.55 times 10 to the 4 kilometers per second. We then divided by the given value of the Hubble's constant, which AQA state on their exam sheet is 65, to get our answer to be 238. Now in the Hubble equation for the constant, the distance is measured in megaparsecs, so that the units are 238 megaparsecs. The next question says, in the middle of the 20th century, there were two competing theories of the universe. In 1964, electromagnetic radiation was observed coming from all directions in space. Figure 2 shows the distribution of this radiation as observed from Earth. The graph provides evidence for one of these theories of the universe. Discuss the main features of this theory of the universe, including the main predictions and evidence for the theory and a suitable calculation. So pause the video now, then unpause the video when you want to go through your answer. Right, again, in answering these questions, answer each bullet point separately. So the first thing is to note that the theory we're considering is the Big Bang theory. So the first aspect you're going to be considering is the idea of redshift, because you'll notice that what's happening is that as distant galaxies are all moving away from us, the further away the galaxy is, the faster it moves. So that links into the idea of Hubble's law. Now the diagram that is shown is the idea of the CMBR. So you'll notice that in this particular image, you'll note that the theory predicts that this black body radiation coming from all parts of the universe at a peak wavelength of 2.7 Kelvin. So you can see on the graph from us that we've got a peak in our microwave region, so it's the cosmic microwave background. So the fact that this is found in all parts of the universe indicates that the universe was once extremely small and extremely dense. Now the CMBR is not predicted by the other theory, by the steady state theory, so therefore it is the radiation that was produced, we're looking at a bit of time after the Big Bang occurred. Now the third bit of evidence that we have to prove the Big Bang theory, even though it's not indicated in the graph, is the ratio of hydrogen to helium in the universe. So we'll note that that the Big Bang Theory predicts that there should be a ratio of 75% hydrogen, 25% helium in the universe in deep space, not in stars, not in galaxies, but just in deep space. And this is actually shown to be correct. Now, the reason why this occurs is that at the early universe, due to the Big Bang Theory, the universe was very hot, very dense, and allowed the hydrogen to fuse into helium, but the universe was cooling down, so it only had chance to do that for 25% of the hydrogen, leaving those ratios to be fixed. So talking about all three bits of evidence for the Big Bang Theory will give you a nice comprehensive answer. The next question says 3C273 was the first quasar to be discovered. IC1101 is one of the largest galaxies known. Table 2 shows some information about these objects. State the property of a quasar that led to its discovery and show that the absolute magnitude of X of quasar 3C273 is about -27. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question you've just got to know what property of a quasar led to its discovery, and that was it was a very bright or very powerful or a very had a high negative absolute magnitude of radio waves being emitted. So it's a high powered radio emitter. Now, to work out your absolute magnitude, we use our equation m minus m equals 5 log d over 10. So what you can do is you've got the distance in megaparsecs, so convert that into parsecs by timesing by 10 to the 6. We've got our value for d. We've got our value for small m, which is 12.8, so we can rearrange and make big M the subject, so we can work it through and we get minus 26.6, so it must be an extremely bright source. The next question says, assume that the quasar and galaxy are both viewed from the same distance. Explain which will be the brighter object and go on to calculate the ratio of the brighter object and of the dimmer compared to the dimmer object. Then the second question says, the black hole at the center of IC1101 has a mass of 7.1 times 10 to the 11 masses of the Sun. Calculate the average density within the event horizon of the black hole. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what you can remember is that the quasar is the brighter one because it has the higher negative absolute magnitude, and the more negative an absolute magnitude, the brighter the object is. So what you do to work out the ratio is find the differences in the absolute magnitude. So we do 26.6 minus 22.8, so we get 3.8. Now, to work out the difference in brightness, we do 2.51 Poisson's ratio to the power of the difference in absolute magnitudes. So it's 2.51 to the power of 3.8, so it's 33. Now the next question is, we're just going to be using the equation that density is equal to mass over volume, but the issue is you've got the mass but you don't have the volume. So the first thing to do is you can work out, because it's a black hole, the Schwarzschild radius. So we do 2gm over c squared. So we pop in all the numbers. Now remember that the mass of the Sun is given to you on the examination sheet, and it's 1.99 times 10 to the 30. So we can find our mass in kilograms by doing 7.1 times 10 to the 11 times by 1.99 times 10 to the 30. We can pop in all the values and we get our radius to be 2.1 times 10 to the 15 meters. Now we'll assume our black hole is a perfect sphere, so we can say that the volume is 4 over 3 pi r cubed, and we've just worked out what r is, so we work it through to be 3.9 times 10 to the 46. Then we do the mass over the volume. Again, it's just the 7.1 times 10 to the 11 times by 1.99 times 10 to the 30 divided by the volume we've just worked out, which is 3.7 times 10 to the 46, to get 3.7 times 10 to the minus 5 kilograms per meter cubed. The next question says, Cepheid is an eclipsing binary system consisting of two stars that orbit their common centre of mass. The primary star is class B, the secondary star is class G. Figure 1 shows the variation of a power magnitude of Cepheid with time as observed from Earth. Explain the shape of the graph in figure 1. So pause the video now, then unpause the video when you want to go through your answer. Right, so in the graph we're seeing that there's dips of a power magnitude, it dips in brightness on a regular occurrence every few days. So the minima of these dips are caused when one star passes in front of the other star in relation to our viewpoint from Earth. Now you get two dips. One is when the bigger star will completely pass in front of the other one, and then the smaller dips, which is when the smaller star will pass in, or the cooler star will pass in front of the hotter star. So you'll see the deeper dips occurring when the cooler one goes in front of the hotter one, and then the smaller dips when you have the vice versa, when the hotter one goes in front of the cooler one. So it's very, very important that this dip size is related to the temperatures of the stars, not their sizes, not their diameters. The next question says, a particular spectral line has a wavelength of 486.136 nanometers when measured from a source in the lab. This line is also present in the absorption spectrum of the primary star of U Cephei. When observed from Earth, the wavelength of the primary star's absorption line varies as shown in the table. State why the average of the values in the table is different from the lab value, and then show the orbital speed of the primary star is about 250 kilometers per second. So pause the video now, then unpause the video when you want to go through your answer. Right, well, you can see why it's different to lab values, because the system is moving in a circle. So you'll see that when it's coming towards us, we're going to get a blue shift, so a shorter wavelength, and when the system's moving away from us, well, therefore you're going to get a longer wavelength and a redshift effect. Now, how do you work out the orbital speed? Well, the first thing to note is we can use our Doppler shift equation by saying Z is equal to the change in wavelength over wavelength. So the first thing to do is work out your changes in wavelength. Now, because we're using this as a ratio, you don't need to convert from nanometers into meters. Well, you could do, it just wouldn't make any difference because it's a ratio. So you find that your difference is going to be 0.413 nanometers. So we'll find the difference and then divided it by 2, because we've gone from maximum to minimum. So therefore our change is going to be gone from maximum divided by 2, if you can think of the image you would get on your wave diagram. We can therefore say Z equals change in lambda over lambda. So we know that our value is going to be the average one. So we're going to go 0.143 over 486.085 is equal to 8.5 times 10 to the minus 4. We can then say V equals ZC. We've got C to be 3 times 10 to the 8, and we've just worked out what Z is. So we get 2.55 times 10 to the 5, or 255 kilometers per second. The next question says, calculate the orbital radius of the primary star, then which absorption lines will be the most prominent in the spectrum of the primary star, and then a different eclipse and binary star system is thought to consist of a white dwarf and a neutron star. Discuss how the astronomers could confirm this. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what can we do? Well, we can see from our graph that in the previous question that the time period of one orbit is going to be 2.5 days. Now we can therefore say that we've got the time period. Now we know that our orbital velocity is going to be distance over time. So the distance in one orbit is going to be the circumference, which is 2 pi r. Then we divide that then by t to get our value for v. So we can rearrange this all to work out what r is going to be. So r is going to be v times by t over 2 pi. So we've just worked out v in the previous question to be 2.55 times 10 to the 5. We've gone from kilometers per second to meters per second. We can then work out what the time is going to be, because we've got to be in seconds now. So we know it's going to be 2.5 days. We convert 2.5 days into seconds by multiplying by hours, then by 3,600, the number of seconds in an hour. We then divide by 2 pi to get 8.76 times 10 to the 9 meters. Now in the question, we know it's going to be hydrogen and helium, because it tells you the class of star in the question, and the class A will have the most prominent lines in hydrogen and helium. Now, how could you confirm the others are a binary star system? Well, it's the idea of what property do you know about a neutron star or a white dwarf? So for white dwarfs, you know that it's going to be an O or B class star, so they'll have lots of hydrogen and helium absorption lines. There'll be a high temperature involved. For neutron stars, you've got a high radio emission, okay, from that particular idea. So what you could do is you could measure the absorption lines, or you can measure the radio emissions, and understand that you're gonna get, if they're in a binary star system, there'll be a point where they eclipse each other and one blocks the other from the viewpoint of the Earth. So therefore you could look to measure the radio absorptions and see if they periodically dip, or you could look to measure the hydrogen helium absorption lines and see if they periodically dip. And if that is the case, you must be in a binary star system. Now, not only is there a dip being important, but also if it's periodically observed, it indicates it's a binary star system. The next question says, type 1a supernovae can be used as standard candles. State what is meant by a standard candle and then sketch on figure 2 the light curve for a type 1a supernova and annotate your graph with suitable scales and a unit for time. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Right, so you answer this question by just firstly learning the definition of what a standard candle is. So a standard candle is an object whose absolute magnitude is known and then its actual distance can be measured as well. Now for this next one, you've got to be able to sketch out a light curve for a type 1a supernovae and have the scales done correctly. So it looks like this. You've got a big dip, you've got a big peak at the start and then it smoothly moves off. Again, we're on scales from about 100 to 300 days. Our absolute magnitude starts at about -12 and then goes to about -20 and you get a peak at about -19, -20 on your graph. You just got to learn what it looks like. The next question says, measurements of type 1a supernovae are used to find a value for the Hubble constant. The distance from Earth is known for many type 1a supernovae. Describe how these values of distance are used with other data to find the Hubble constant. Your answer should include the other data needed and how this data is used, the graphs plotted including appropriate units for axes, and how the Hubble constant is obtained to any limitations on the result. So pause the video now, then unpause the video when you want to go through your answer. Right, again, for this type of question, you've got to address each bullet point separately, so you write your answer in a logical order. So let's consider what other data is needed. So the first thing is you'll also need the redshift, which is a value of z. Now again, z can then be used to find the velocity of recession of this object by doing v is equal to zc. Now again, you can work out the value of z by measuring the wavelength of the spectral lines and comparing them to the standard lab value and having z equal the change in lambda over lambda. The graph you would then need to plot is the one that Hubble plotted, and that is the graph of velocity on the y-axis and distance on the x-axis. Hubble used velocity in kilometers per second and distance in megaparsecs, and then when you draw that graph, your gradient will be the Hubble constant, h, and then how you can work it through. Obviously, if you switch over the axes, the gradient will be 1 over h. Now, the limitations of this particular method is that the value of apparent magnitude, can therefore be affected very easily by other objects blocking out values, blocking out the light, as it goes through it. For example, like a gas cloud, a dust cloud, comets, etc. There's going to be lots of variation in the data due to random errors in measurements, or just variations in galaxies, or just variations in type of different astronomical objects. The idea that at large distances, which we're using, that the acceleration of the universe due to dark energy will also affect your results, and we don't know how it will really affect the results, so that's going to be important. And also you need lots of data from different supernovae to actually get this, and supernovae are quite rare events in the universe, so as a result it's quite difficult to do, and so therefore all these different random errors will lead to be very difficult to actually draw the correct gradient for the line of best fit in your graph to determine the Hubble constant. So that brings an end to today's revision session. If we've been successful and we've learned in today's revision session, we've been able to answer A-level physics examination style questions, assess our understanding of A-level physics, and understand what topics we need to improve on for the AQA A-level physics. So thank you very much for watching this revision session on Astrophysics for AQA A-level physics paper 3. Thank you very much and have a lovely day.